Hello everyone, and welcome to this presentation called Related Conservation Drainage Practices. I'm Jane Frankenberger, Professor of Agricultural and Biological Engineering at Purdue University, and this presentation will cover the following topics. First, we'll talk about subirrigation, then we'll talk about a number of conservation drainage practices that work right in the field, then we'll talk about denitrifying bioreactors, saturated buffers, constructed wetlands, and two-stage ditches. This module is part of the series of distance education modules on drainage water management. Specifically, it helps you think about how other drainage practices might fit into a conservation plan. The first practice I'll discuss is subirrigation. This is a little different than the other conservation drainage practices, but we wanted to include it to make sure that you understand the difference between drainage water management and subirrigation. Subirrigation is a method of irrigation that delivers water to the plant root zone from below the surface, and we often talk about it together with drainage because the same tubing that's used to drain the field during the wet times of the year can be used to deliver the water in dry times of the year when irrigation could really be beneficial. Subirrigation requires the field to be divided into zones just like drainage water management. In this slide, which you may recall from Module 6, which was on drainage water management layout, the field has two zones. Zone 1 has laterals roughly parallel to the contour, and Zone 2 has a main drain roughly parallel to the contour and then laterals perpendicular. Each of the zones has a water control structure, these red rectangles. For drainage water management, water in the field flows into the control structures, and if the outlets are raised, some of the water is held back. When the same drainage system is used for subirrigation, water is instead added to the control structures, and the higher water level in the structures pushes water back up into the main drains and into the laterals. And from there, as long as there's a fairly impermeable layer below the drains that holds the water table up, the water table will rise and the water can be used by the crop. Here's the same situation for Zone 1. For effective subirrigation, the water table should be fairly uniform, so that's one of the challenges. Water table, of course, rises the most when it's directly over the tiles, as you can see in the top graph. And in the photo of the cornfield below that from Missouri, you can see very dramatically how effective subirrigation was right over the tiles and how much less effective it is in between. So that means that subirrigation works the best when we have highly permeable soils, allowing the water to spread out, over an impermeable layer that keeps the water table high. Now, if we don't have those conditions, we can just use very narrow spacings of the laterals, and that, of course, increases costs. Of course, you need a water source for subirrigation. Usually this would be a well, or it could be surface water if there's one that's reliable even in dry times of the year. An innovative alternative in our wet tile drained areas would be to store some of the water when it's drained rather than letting it go into the ditch and eventually into the Gulf of Mexico or the Great Lakes downstream. This type of system can be called water recycling, and in addition to the yield benefits that are similar to other irrigation systems, this system would have the added benefit of reducing drain outflow and thereby improving downstream water quality. So it's a system with many advantages. Unfortunately, there's one big disadvantage, and that's the cost, both in infrastructure and the land needed for the storage reservoir. But especially as the climate becomes more and more variable and the risk of drought potentially increases, the benefits may start to outweigh the costs. So we shall see. So now we'll turn to the conservation drainage systems, which, while they maintain and in some cases potentially improve crop productivity, the main focus is on reducing nutrient losses from the drainage system. And I also wanted to add, when we say nutrients, we're talking about both nitrogen and phosphorus. Most of these systems were particularly developed for nitrate reduction, which is such an issue in tile-drained areas. As you know, tile drains are installed for many good reasons. These are the intended effects. Among these are that we have more timely planting and increased yields, and that it can decrease surface runoff, soil erosion, and the loss of nutrients through these pathways. Unfortunately, there are also the unintended effects of tile drains. Among these is especially that they greatly increase the loss of nitrate to the streams. So the arrow shown there reminds you that when you see flow out of a tile drain, it almost always carries quite a bit of nitrate. In more recent years, we've been finding that some phosphorus also moves through the tiles. It's a much smaller amount, which I've tried to illustrate with a smaller arrow. In fact, it would be an arrow even much smaller than that, but I was afraid you couldn't see it if I made it too small. There is some potential for both of these. One way to think about these conservation drainage practices is to separate where they work. So some of them reduce nutrient loss actually in the field. Others work at the field's edge when the water is already in the tiles, and some of them work downstream in the ditch or the stream or in a wetland, as we'll see in a minute. So we're going to start with the practices that reduce nutrient losses in the field. Now, these are not always thought of as conservation drainage practices because some of them are just good nutrient management practices, but that's one of the best ways to, in fact, reduce our nitrate loss or nutrient losses is to use practices like nutrient management, 590, cover crops, and a conservation crop rotation. And then we'll also turn to drainage water management, which you've already learned about. One of the good illustrations of the potential to reduce nitrate in tile drains through these in-field management practice is a long-term study by Dr. Eileen Kladivko at the Southeast Purdue Ag Center. When she started out, back in the 80s, the typical recommendation was to add 250 pounds of nitrogen per acre and continuous corn. And you can see that the nitrate levels that came out were typically in the 30s, more up around 30 milligrams per liter. In 1990, she reduced the amount of nitrogen applied per acre, and the rates of the loss concentration went down. And finally, in the later 90s, she changed to a corn-soybean rotation. She added a cover crop, and she reduced the nitrate levels further, and as you can see, there's a very dramatic and wonderful decrease in the nitrate that came out of it, down below 10 in most years. So that doesn't show necessarily that we need to have all the practices, but it does show the benefits of the practices in the field in reducing nutrient losses in the tile drains. Drainage water management, which you've already seen, I'm just going to remind you of it, is another in-field practice that allows us to decrease nitrate losses. If we have the tile drain, saturated soil below it, the drainage that's coming out to the ditch, during the winter we can hold the outlet high and the water table rises when the drainage is not needed. Before planting, we can lower it, and in the summer raise it again partway to add crop benefits. So those are the in-field nutrient loss strategies or conservation drainage strategies. Now we're going to turn to those that work at the edge of the field. And the first one is the practice called denitrifying bioreactors, or as I usually call them, woodchip bioreactors, because I think that's clearer and conjures up the image of what they do. And there is an NRCS interim conservation practice standard 747 that's available in some states. This is still a practice that's being developed and tested, but there's more and more demonstration sites that can give us insight. So the Woodchip denitrifying bioreactor is basically a large subsurface trench, or more like a hole or a pit, that's filled with a carbon source, usually wood chips. And the way it works is that the tile drain water, shown here, is diverted. Instead of just flowing out to the stream, it's diverted using this control structure into the bioreactor. At the same time, we always need to have an overflow that allows water, if it's flowing in at too high a rate, to go directly to the stream. The wood chips provide both habitat and food for the all-important denitrifying bacteria, and it's those bacteria that actually treat the nitrate. Denitrifying bacteria need several things. They need food, which is the carbon in the wood chips. They need a place to live, which the wood chips provide. They need anaerobic conditions, which is provided when we're able to hold the water table high enough that the wood chips are saturated. And then they need the nitrate to breathe. And when they do that, they denitrify the nitrate, which is NO3, through a number of intermediate pathways into N2 gas, which is the most common element of our atmosphere and quite harmless. So it's a wonderful process. So how large do bioreactors need to be? I won't go into detail on design here, but basically they need to fulfill two objectives. First, to have a sufficient retention time in the bioreactor to treat the nitrate, and then to have the capacity to treat a reasonable proportion of the flow. So that ends up that they're quite large. The interim standard 747 that's currently in use in Illinois, at least, gives several different alternatives. I've listed two of them here, a couple. One is to treat 15 to 20% of the peak flow. Another is to just treat 10% of the peak flow if monitoring will be taking place, or to look at it in terms of the long-term average annual flow and treat about 60%. There are sizing tools available through Iowa State University, the University of Illinois, and Illinois NRCS. There may be others by the time you see this. The other thing I wanted to show was Dr. Richard Cook in Illinois has developed this bioreactor performance curve, and he plots loading density on the x-axis of acres per 100 square feet of bioreactor versus the amount of load reduction, and encourages the design in this part of the curve. Another way to look at it is that roughly 0.1%, or a tenth of a percent, so from 0.5% to 0.14% of the field being treated. So just as one example, if you had a 40-acre field, you would need somewhere around 850 to 2,000 square feet. But there's a lot of, as I said, there are many demonstrations available now. One is from Illinois, and these photos are available on the web. They installed a bioreactor in the buffer. Here you can see the ditch, and they put the water control structure here to intercept the tile drains, and then it goes into this fairly large hole, which then gets lined with plastic. And the purpose of this tile is to spread the water out across the entire bioreactor, and then it gets filled with wood chips. Another example from Iowa, and these photos are from Iowa State University. Here is one that's a little smaller, but also in a buffer. The hole is dug, the tiles are laid to spread out the flow, and the wood chips, which here come in a large semi, as you can see, are spread. Here they're all spread out to a level, and then it's covered with soil so that this can be replanted. So denitrifying bioreactors are wonderful. They're very effective at treating the amount of with the water that actually flows through them, but they do require a lot of wood chips. Many people often ask about their lifetime. It's not yet known, but we know that it's greater than 10 years. I don't think any of them have failed yet. The next conservation drainage practice I'll be discussing is what's commonly called the saturated buffer, or sometimes resaturated buffer. The interim NRCS standard is available in only a few states, actually calls this vegetated subsurface drain outlet. The saturated buffer is an innovative practice that takes drainage from the field, and instead of allowing it to continue in the subsurface under the buffer, essentially nullifying the potential treatment of the buffer, it as shown in the right, it adds a control structure at the edge of the buffer and pushes the water into additional tubing that is laid along the upstream side of the buffer. There is an overflow discharge if more flow is needed, but most of the flow is going to go into these two tiles and work its way along the buffer so that it spreads out and makes the whole buffer saturated. The genius of this is then it allows the buffer to use the process of denitrification or plant uptake to fully function to take up the nitrate. Here's a photo that might allow you to see a little bit more clearly how this process works. You can see the corn upstream and the drainage from the field coming into the control structure from there. The raised outlets push the water into perforated tubing or drain tile on both sides of the control box so that it then resaturates this buffer that you see with trees on the right side. This is the same site now shown on an aerial photo. This is the control box in this area here that receives water from the field tile and sends most of it in one direction or the other along these distribution tiles on the upstream side of the buffer. And in this case, the buffer is a beautiful forested buffer. It could also work well with grass. The effectiveness of the practice has been monitored by Dan Janes of the USDA Agricultural Research Service. They found that for the water that actually flows through the buffer, nearly all the nitrate is treated. Now that sounds great, but unfortunately it's difficult to design a system in which all the water can actually flow through the buffer. The flow is limited by the permeability of the soil. More water simply can't flow through the length available, and the length is limited by, in this case, the length of the tile feeding the saturated buffer was limited at both ends by field tiles. There's one here and one here. So this 900-foot length was all that was available. Also, because the distribution tiles can't handle all the water during peak flows, there's an overflow drain that provides an alternative pathway for drainage water so that it doesn't back up in the field. So the drainage works well under all conditions, but the water that flows through the overflow drain is not treated. So that's a limitation of the saturated buffer that it's important to understand. Research so far has been quite limited, but about 15 additional saturated buffers have been installed and are being monitored, so we'll know more about this practice in coming years. Constructed wetlands are a conservation practice with many benefits. When used as a conservation drainage practice, they consist of a shallow basin with vegetation constructed to intersect and treat the flow of contaminated runoff, or in this case, drainage water. Constructed wetlands can remove nitrogen and phosphorus through three methods. The plants can take it up, denitrification, which we've talked about before with the Woodchip bioreactors, or reducing the total volume of drainage, and usually all three of these take place. So let me talk about them. The wetland plants contribute to water quality because they use the nutrients that are in the water for plant growth. This process is called plant uptake, and it moves the nutrients out of the water and into the plants. And if they're harvested, then that takes them out of the system. The next method of treating nitrate is denitrification. As you recall, this is the process where denitrifying bacteria change the nitrate to harmless nitrogen gas in the process that starts out as nitrate and ends up as N2. The third process is actually reducing the volume of drainage, and wetlands can do this through infiltration. Some of the water, as it's sitting in a wetland, can actually infiltrate or seep into the ground. There will also be increased evaporation over a system in which the water flows directly out into the ditch or stream. And also the plants will use some of the water and transpire it. So all of these result in water quality benefits as the drainage volume is decreased. Wetlands, of course, have a cost, and one of the costs is that they take quite a bit of land out of crop production. Researchers at Iowa State found that 0.5% to 2% of the total watershed area should be in a wetland to really effectively reduce the nitrate. So you may remember the bioreactor uses a much smaller percentage. It was more like 0.05, but the difference is that wetlands have many other benefits. For example, they provide habitat for wildlife, they provide beauty in the landscape, and so the public often funds this amount of land, which is increased by also the need for a buffer, so that all these benefits can come about. The final practice I'll be talking about is called the two-stage ditch. It's another downstream practice and is not yet widely used or cost-shared by NRCS. There is the practice 608 can possibly fund this, and in Indiana it's the 582 open channel standard that is used for two-stage ditches. Basically, two-stage ditches can increase the ecological function of drainage ditches while maintaining or even increasing their drainage function. And two-stage ditches do that by keeping the inset channel the same as before construction, but adding this second stage that consists of benches that are really miniature floodplains within the channel of the ditch. And in that way, when there are high flows, the water is able to go out on the benches, essentially mimicking natural streams, which are able to go out on their floodplain. And this makes them more stable and also assimilates nutrients. Two-stage ditches are described in the National Engineering Handbook, Part 654, which is the Stream Restoration Design Manual. And it's Chapter 10 that's all about two-stage channel designs. And this figure shows the conceptual image of what the two-stage channel or two-stage ditch is attempting to do. Just as we saw in the past slide, there's a floodplain channel which is almost always wet, and then there are benches where the water can go up during times of higher flow. In Indiana, the open channel standard has been used and describes this two-stage process or two-stage ditch design by explaining additional criteria for conversion to a two-stage ditch. So while ditches like this, with this trapezoidal format and even armed by riprap, these kind of ditches were once standard, and in fact these were supported by Indiana NRCS practices in the past. We now expect our ditches to have more function, to actually treat nutrients while maintaining the drainage. And this kind of a ditch filled with that wonderful vegetation of all kinds, it has a meander there, and there's so many ways that the ecological function can be improved through denitrification and assimilation of nitrogen or phosphorus. Now, I often show this picture to farmers and drainage contractors in my state and ask what they think, and the most common thought is that this looks really messy and they want to get in there and clean it out. So it's really a shift in mindset, and the two-stage ditch is just part of it, but the idea that our ditches themselves can be richer ecosystems and have true ecological functions is really a path forward as far as treating our nutrients. The Nature Conservancy has really been the leader in getting two-stage ditches constructed. Here's the shadow ditch in Indiana, which they constructed several years ago and has been monitored by Notre Dame. This is the before construction, and then this is after construction. So basically, if I go back, you see that the meanders remain exactly the same. They're not changed, but the banks are pulled back, and so there's the benches and there's also a shallower slope. We can notice that ditches, when left alone, often do start to form a two-stage ditch, and this gave an original clue to Dr. Andy Ward at Ohio State, who originated this concept. And studying, or looking at least, at the ditches that exist now with benches is really helpful in understanding how to design them. The dashed blue line is a typical surveyed cross-section of an existing ditch, and the red line is the shape that it will be after excavation. This is using spreadsheets that were designed in Ohio and have helped many people in designing their ditches. To better understand the process of constructing a two-stage ditch, I thought I would include a little video from the construction of the two-stage ditch on a Purdue research farm. It was done by the Land Improvement Contractors Association as a field day, which had an educational purpose both for the public, who was invited to watch at any time, and also for the contractors themselves, none of whom had done a two-stage ditch before. So there's a little more machinery in this video than you would see at a typical excavation. So notice how the excavators stay on the banks at all times and don't touch the main channel of the ditch itself. This ensures that the vegetation and stream channel bottom, which are in contact with the aquatic life of the stream, are not directly affected. And this is also done so that a Clean Water Act permit from the Corps of Engineers is not required, although the requirements may be different in other cases. Another thing to notice is the large amount of spoil dug out of the ditch channel. This is unavoidable and, in fact, is one of the barriers to two-stage ditches at many sites. On this project, the spoil was simply feathered out over the entire buffer width, and you see the bulldozer and other equipment working on that. We were fortunate to have a wide buffer. Depending on the soil quality, it may also be spread out on the cropped fields. One thing that's clear from the video is that constructing a two-stage ditch is not a small project or low-impact project. It's a major construction project that leads to considerable temporary disturbance. However, the projects that have been implemented have all led to greater stability of the channel in the long term, as the wider channel with floodplain benches allows the more natural fluvial processes in the channel. So once again, the two-stage ditch increases the ecological function of drainage ditches while maintaining or increasing their drainage function. Two-stage ditches are more stable. They allow for more denitrification in the benches to reduce nitrate, and they appear to lead to improved water quality, although more research is needed. In this module on related conservation drainage practices, we looked at practices that reduce nutrients in the field, at the edge of the field, and downstream. Specifically, we discussed how subirrigation requires zones like drainage water management, but also a water source. how the wood chips in a denitrifying bioreactor provide habitat and food for the bacteria that convert nitrate into atmospheric nitrogen, and how saturated buffers recreate some of the nutrient-reducing functions of a buffer. We also reviewed constructed wetlands that reduce nutrients through plant uptake, denitrification, and reduction in drainage volume, and the two-stage ditch, which provides a wider channel than typical narrow trapezoidal channels and therefore improves their ecological function. Together, these practices provide many options for landowners, many tools in the toolbox to reduce nutrient loads from our drained agricultural lands. Thank you.